First of all, I want to express my gratitude to the members of the jury for being present here today. And thanks to all of you, ladies and gentlemen, for attending my PhD public defense. Today, finally, I have the opportunity to give a general overview of what I've done in the last 4 years and a half here at the VUB in the context of my PhD defense. And I will do it through a presentation which is entitled Hidden Semi-Markov Models for Online Failure Prediction of Industrial Machines. But before starting, let me make some consideration about the meaning of failure prediction. So we all know that the majority of the equipment around us, sooner or later, they are going to fail. So they are going to break down. And in the majority of the cases, they are going to do it suddenly, so in an unexpected way. Now, I invite you to imagine for one moment if we could be able to predict, so to, let's say, forecast when these failures are going to happen. So what we could do, for example, is to plan an intervention just before the failure happened in order to avoid the inconvenience deriving from the misusage of this faulty equipment. And actually, this is the main idea, the main concept of my PhD research. And if we bring this idea to an industrial setting, we have that, in principle, accident like this could be avoided. And I'm sure that all of you remind the episode of the picture, that is the explosion of the Deepwater Horizon platform that happened in April 2010, which still today is considered as one of the biggest environmental disasters of the history, in which 11 people died, and British Petroleum experienced a huge economical loss. So what companies normally do in order to avoid this accident is to perform maintenance on their equipment. And despite being essential in order to maintain equipment in good condition, maintenance is a very, very expensive activity because a part of the maintenance cost itself, generally it requires the stop of the production while maintenance is performed. And because maintenance is so expensive and let's say consequence of the accident deriving from the bad maintenance can have such a big impact on companies, we have that optimized maintenance strategies can enable companies to have a potentially huge cost reduction. And this fact is confirmed by a recent study that has been published by the McKinsey Global Institute that states that optimizing maintenance planning can generate savings of up to $400 billion a year. So generally, we have 3 types of maintenance strategies. We have preventive, corrective, and predictive maintenance. Concerning the first one, the preventive maintenance, it takes the form of a scheduled maintenance that is performed at a regular time interval, and it is performed regardless the actual health condition of the machine. So one of the biggest problems of this maintenance strategy is that it doesn't take into account the real necessity of an equipment to be maintained. So in principle, it can happen that a component that it is still in a good health condition, it can be maintained or even replaced. And this represents an economical, let's say, loss. The second maintenance strategy is the corrective maintenance, which actually is the easiest one because it lets the machine running until the failures occurs. When, after the failure happened, then maintenance is performed in order to repair the machine. So in order to restore the machine to its original functioning. And you may agree with me that one of the biggest problems of this strategy is that the severity and the consequence of the failure are not predictable. So in principle, catastrophic event like the one I showed you at the beginning of the presentation can happen. So in this work, we use the third maintenance strategy, which is the predictive maintenance, that outperforms the other maintenance strategies since it aims to predict the exact moment in time in which an equipment is going to fail in order to perform just-in-time maintenance. So maintenance when it is actually needed. Predictive maintenance is performed in 2 steps. The first is the diagnostic. in which the current health condition of the machine is estimated, while the second is the prognostic, in which the degradation of the machine is projected into the future in order to estimate how long my system will resist before failure. So what is called the remaining useful lifetime estimation. And it is obvious that accurate and precise estimations in these two steps are essential to enable companies to perform an effective predictive maintenance. For this reason, my work concentrates in three main areas. The first is the diagnostic, the second is the prognostic, and the third is the online learning, which is essential if we want to keep high the predictive performance of our methodologies in presence of not stable conditions. So concerning predictive maintenance, in the literature there exist several approaches that are able to implement it. So in this work we use a data-driven approach because generally industrial machines are already equipped with sensors that are placed in a critical part of the machine. And they're also equipped with, let's say, with monitoring systems that are able to record and collect and store monitoring data, like, for example, temperature, pressure, or vibration. And these monitoring data are used to learn the parameters of a behavioral model, which virtually replace our system, and can be used to perform our estimation. So we have that one of the biggest advantage of data-driven approach is that for well-monitored system, we can consider the model as a black box. So we don't need a deep knowledge of the system internal functioning in order to model the machine. And this is a very big advantage, especially for complex systems like industrial machines. Concerning data-driven approaches, the most commonly used models are, for example, dynamic Bayesian networks, supervector machines. However, in this work, we used state space model like hidden Markov and hidden semi-Markov models because we assume that during its lifetime, a machine proceeds along several health conditions from a normal one to a worn until the failure of the machines. And we also assume that the sensorial measurements are correlated with the state of the machine. So the sensorial measurements can tell us something about the condition of the machine. Actually, this behavior maps quite well with a state space model, like a hidden Markov model, because in hidden Markov models, we have two types of variable. We have the hidden state variable that represents the not measurable condition of the machine, and we have the observation variable that represents the sensorial measurements. Moreover, in the majority of the case in this work, we used a left-right topology of hidden Markov model because we assume that the degradation pattern of the system under study is monotonically increasing. So we assume that a machine can degrade more and more, but it cannot recover by itself. Concerning the parameters of our hidden Markov models, they are the initial state probability that actually gives the probability of the initial condition of the machine. We have the state transition probability that rules the dynamic of the state transition. And finally, we have the observation model that, depending on the nature of the sensorial measurement, it can be continuous or discrete. So concerning the diagnostic, the first part of my work, we perform an introductory study in which we introduce a methodology that is based on the combination of hidden Markov model and a change point detection algorithm, which is able to perform the initialization of the model parameters and the number of the states, as well as to perform an adaptive condition assessment. So we have that one of the problems of the state-of-the-art hidden Markov models is that the states are fixed a priori, normally by using expert knowledge. And the parameters of the model are also initialized at random. And this random initialization may lie far from the optimal point of the parameter, leading to a slow convergence of the learning algorithm to a point which can be also not the optimal one. Moreover, once we learn the model on a given training set, we have that this model is able to recognize only the conditions that are included in the training set. So it means that if we take this model to perform condition assessment on a new system that experience conditions that are different for what were included in the training set, this model won't be able to recognize these new conditions. So what we propose in this work to solve these problems is the combination of the model learning with the change point detection algorithm. So the change point detection algorithm is a data mining state-of-the-art algorithm which has been proposed in two versions, the batch and the online change point detection algorithm. So we first use the batch CPD to perform the initialization of the number of the states and the parameters of the model. And afterward, we use the online CPD to perform the detection of unknown conditions. Concerning the batch change point detection algorithm, it is an algorithm that is based on curve fitting. And it aims to provide a segmentation of the input signal. And thanks to this segmentation, we can have an idea. So we can initialize the number of the states. Moreover, always based on this segmentation, we can also initialize the parameter of the model by using simple counting formulas. So in this slide, I show you the results we got by applying this batch change point detection algorithm to the bearing monitoring data belonging to the NASA dataset. And actually, we applied this change point detection algorithm to several bearings that, during their lifetime, they didn't experience failure. And what we obtain, as we can see from this figure, are two segments. So we initially used a two-state hidden Markov model. Moreover, thanks to the proposed initialization of the parameter, we obtain a faster and accurate learning procedure if compared to 10 other random initialization, as we can see from these two bar figures, in which the first one represents the numbers of iteration needed to the learning algorithm to reach convergency, while the second, the bottom one, represents the goodness of the model fitting, and the orange bar represents our methodology. So now what we have a two-state hidden Markov model that is based on bearings that during their lifetime they didn't experience failure. So it means that if we take this model as it is and we perform condition assessment on a bearing that in the end of its lifetime fails, this model won't be able to recognize this failure of the bearing. So here is where the online change point detection algorithm comes into play, because the online change point detection algorithm is able to recognize in real time when the system changes condition. So in order to test this methodology, we apply this online change point detection algorithm on a bearing that in the end fails. And as we can see from this small animation, we have that at the beginning, the original two-state hidden Markov model is able to correctly recognize the first two conditions. And as we can see, when the bearing switch from condition 1 to condition 2, the change point detection algorithm, the online version, is able to recognize this event, as we can see from this green cross. However, as I said before, at a certain moment, this bearing experiences a severe degradation modality that will bring the bearing to fail. And of course, if we continue to use this two-state model, we won't be able to recognize the failure of the bearing. So what happened is that at a certain moment, the change point detection algorithm is able to detect the severe degradation that the bearing experiences, as we can see from this red cross. And what we can do now, because we are using a left-right topology of hidden Markov model, we can add a third state, which represents the new previously unknown condition. And from this moment on, this model is able to correctly recognize also the failure condition of the bearing until the end of the experiment. So in conclusion, if we combine the online change point detection algorithm with the model, we enable the hidden Markov model to have a variable state space. So this was concerning the diagnostic. Now, if we want to effectively face the prognostic problem, so the problem of prediction of future failures, we cannot use hidden Markov model because it is a well-known fact that one of the biggest problems of hidden Markov model is the fact that the state transition is modeled by means of a constant transition probability matrix, which induce a geometrically distributed state duration, which is actually not suitable and not effective to model the majority of the real-world application. Because if we use hidden Markov model, we assume that the probability that a system has to fail at a given moment is always constant, regardless how long the system has been running, which is not the case of the majority of the real-world systems. So an extension of hidden Markov model is represented by the hidden semi-Markov models, that by explicitly modeling the state duration, it is most suitable to be used for systems that are dependent from the time. And this fact is shown by means of a simple example in which we generated a signal for which, as we can see from this figure, just by looking at the observation, is not possible to distinguish between state 1 and state 2 because we use the same observation model. And indeed, the Viterbi algorithm, so the state recognition algorithm of the hidden Markov model, fails in detecting the state 2, which is wrongly confused with the state 1, as we can see from the middle plot here. On the other hand, we have that hidden semi-Markov model. By combining information coming from the observation signal and the state duration, obtain much better performance in discriminating between the states. So concerning the specification of the model, we have that similarly to HMM, hidden semi-Markov models has two types of variables. So we have the hidden state variable representing the condition of the machine, and the observation variable representing the sensorial measurement. And on top of that, as I said before, the state duration is explicitly modeled by means of a probability distribution. So it means that hidden semi-Markov model take into account how long the system has already been in a certain state to determine if, let's say, a transition to a new state is more or less probable. So in easy word, we have that by using hidden semi-Markov model, we can effectively face the aging factor of the machine. Concerning the parameters, also in this case, we have the initial state probability. Compared to the hidden Markov model, with hidden semi-Markov model, the state transition probability is replaced by a non-recurrent transition probability, which rules the dynamic of the state transition when a transition actually happened. Also in this case, we have the observation model that can be continuous or discrete, depending on the nature of the observation. And in this work, compared to the majority of the state-of-the-art work, we modeled the state duration by means of a parametric distribution, which has advantages in terms of less parameter to be estimated. Moreover, we don't impose any constraint on the nature of the function of the distribution. So as I said before, the peculiarity, so the key aspect of hidden semi-Markov models is that they take into account how long the system has already been in a certain state to determine if a transition to a new state is more or less probable. So it means that in order to have good modeling precision, a good predictive performance, it is essential and crucial to correctly estimate how long the system has already been in a certain state. And at this purpose, in this work, we introduced a new and improved induction formula, which is able to calculate, to estimate the time that the system has spent in a given state Si prior to the current time. And this formula is the multiplication of two factors, in which the first one represents the probability that the state at the previous time was already in this given state Si, assuming that the system is in state Si at the current time, multiplied by the previous state duration estimation incremented by 1. Because in case of certainty, let's say the duration estimation is simply the previous estimation plus 1. So this is the formula we introduced. And actually, we derived it straightforwardly from the definition of the expected value. And as we can see from this slide, this formula can be also expressed in terms of the parameters of the model and in terms of the forward variable alpha. And if we compare this formula to what proposed in the state of the art, we can notice that our proposed formula is a little bit more complex than the state of the art. However, as we will see soon, it obtains much better results in terms of accuracy of remaining useful lifetime estimation. So after we introduced the new induction formula, and after we defined the explicit duration of the model, we extended the learning and the inference algorithm from the hidden Markov model to the hidden semi-Markov model in order to deal with this explicit duration model of the hidden semi-Markov model, but more importantly, in order to effectively face the prognostic problem, the more complex prognostic problem, and in particular, in order to face the remaining useful lifetime estimation, for which if we use hidden semi-Markov model, at first we have to identify among the states of the model which one represents the failure state. Once this failure state is identified, then the problem of remaining useful lifetime estimation is, let's say, defined as the calculation of the expected time that the system needs to reach this failure state. And as I said before, this is performed in 2 steps. So at first, we estimate the uncertainty related to the current state. And to do this, we simply calculate the probability of the current state. And we do this simply by using the parameters of the model, so the delta variable of the Viterbi algorithm. After that, the estimation of the expected remaining time in the current state is performed. And this task is made easier by the explicit model of the duration of the hidden semi-Markov model. Indeed, what we have to do is simply to estimate a sum which is weighted by the uncertainty of the current state. And this sum is simply based on the mean parameter of the duration distribution and on the state duration estimation that I introduced a few slides ago. Moreover, we have that an important fact is that we can provide also a confidence interval, so a lower and a upper bound of our average estimation, simply by adding or subtracting the standard deviation parameter to this estimated quantity. After that, a predictive step is performed, which goal is to estimate the probability of the next state. And also this can be easily done by the model parameters. After that, the estimation of the intermediate time and the predictive step are, let's say, repeated cyclically until the algorithm detects that the system entered the failure state. Then at this moment, the remaining useful lifetime is simply obtained by summing all the intermediate estimated time. Then another problem that we tackled under the context of prognostic was the automatic model selection, which problem is to select an appropriate model structure which is effective to describe the data. And the structure should be as less complex as possible in terms of number of states, in terms of complexity of the observation model, but also in terms of the correct duration distribution. And in this work, in order to solve model selection, we propose the usage of the Akaike information criteria, which has been extensively used and studied for hidden Markov models, but not for hidden semi-Markov models. And the goal of Akaike information criteria is, it optimizes, let's say, the model of the structure of the model by minimizing a 2 terms expression, which goal is to find a compromise between the goodness of the model fitting, which is represented by the model likelihood, and the model complexity, which is represented by the number of the parameters needed to describe the model. Then this quantity is simply divided by the total length of the data. So in order to test the effectiveness of this methodology to perform automatic model selection, we perform several experiments, both on simulated and real data. So at first, the first simulated experiment that we perform has been performed by using a hidden semi-Markov model, by generating data with hidden semi-Markov model with 5 states and different observation types, so continuous and discrete, and also different duration distribution. And as we can see from this figure, the minimum value of the AC doesn't always correspond to the correct structure that has been used to generate the data. However, it is clear that the AC value reaches a plateau in correspondence to the correct number of states. And this was the correct number of states that we selected. Moreover, we have that in order to be more, let's say, more robust, it is needed a methodology that is able to detect automatically when this plateau happens. In any case, we have that within the correct number of states, the Akaike information criteria is always able to select the correct duration distribution. So we applied the Akaike information criteria also to a real use case. In this case, we used the Pronostia bearing monitoring data. And the optimal structure that was returned by the Akaike information criteria was a hidden semi-Markov model with 4 states and a Weibull duration distribution. And actually, this structure gave us the best results in terms of accuracy of remaining useful lifetime estimation. Concerning the remaining useful lifetime estimation, we also here performed several experiments, both on simulated and real data. So these slides show an example of simulated experiment, in which in this figure we have that the black solid line represents the true remaining useful lifetime, while the gray bold line represents our average estimation together with the upper and the lower bound. And as we can see from this figure, the estimation performed was quite accurate. And in order to numerically estimate the goodness of this estimation, we consider the average absolute prediction error, And as we can see from this slide that represents one particular experiment that I performed in my dissertation, we obtained quite low values of average absolute prediction error. It means quite accurate remaining useful lifetime estimation. And the goodness of these results is even more evident if we compared to what we obtained by using the state-of-the-art formulation for the remaining useful lifetime estimation formula and for the state duration estimation, for which is clear that much higher values of average absolute prediction error is obtained. Then we applied also our estimation to a real use case, again on the pronostiability monitoring data. And as we can see from this figure, also in this case, we obtained quite accurate estimations. And in terms of average absolute prediction error, we obtained values of around 1 hour, which is a satisfactory result if we consider the limited amount of data available, but also the high variability in the bearing lifetime. Finally, the last topic we tackled in my work was the online learning, which goal is to obtain an adaptive model. Indeed, we have that industrial machines are extremely non-stationary systems because they are constantly operated under variable conditions. And these variable conditions are caused, for example, from changes in the environment or from changes in the operating condition. And moreover, we can also have the case in which a brand new machine is acquired for which no historical data is available. However, we can have a prior knowledge on this machine coming, for example, from a similar machine. So in all these cases, rather than using an offline learning, which can be also not applicable, it is needed a methodology that is able to continuously re-estimate the parameters of the model while the system is normally functioning. So each time a new observation is collected. Concerning the literature related to the online learning of hidden semi-Markov model, it is quite limited. So what we did is to take a state-of-the-art approach based on the gradient descent. And when we use gradient descent, at first we have to define an objective function, which in this case is represented by the log likelihood increment related to the last collected observation. Then the goal of the online learning algorithm is to re-estimate the parameters of the model in order to maximize this objective function. And this is performed by means of a recursive estimation formula, which starts from an initial guess, and each time a new observation is collected, the parameters are re-estimated by adding to the current vector of the parameter the gradient vector, which represents the growth direction of the objective function, and it is obtained by calculating the derivatives of the objective function with respect to the all model parameters, multiplied by a positive step size that in this work, compared to the state of the art, has been optimized by using a line search that in the discrete interval 0, 1 finds the value of the step size that maximizes the entire model likelihood. So also in this case, in order to evaluate this methodology, we performed several experiments, both on simulated and real data. So the first experiment has been performed with the idea of simulating the case in which a brand new machine is acquired, for which just a limited prior knowledge is available in terms of the parameters of the model that is represented by this non-accurate initial guess, coming, for example, from a similar machine. Now, we turn on our new machine, and the goal of this experiment is to test if indeed the online learning algorithm is able to perform an estimation of the parameters that, starting from this non-accurate initial guess, is able to converge to the true parameters of the model, which in this case, because we simulated the data, are known. And this figure shows how nicely the estimation performed by the online learning algorithm converges to the true values of the parameters. The second experiment has been performed with the idea of simulating the case in which the operating condition of the machine change. And this fact has been simulated by using a hidden semi-Markov model for which at a certain time, in this case t equal to 5000, there are several parameters that change. And this aspect is reflected by the changing of the shape of the observed signal, as we can see from this figure. Also in this case, as we can see from this figure as well, the estimation performed by the online learning algorithm is able to track the changes happening in the true parameters of the model. Finally, we tested our online learning algorithm to a real-world use case. Again, we used the pronosticability monitoring data, where several run-to-failure experiments has been performed on bearings under two different conditions. And these two conditions differ between them in terms of different rotational speed and different load applied on the bearing. Then the goal of this experiment is to test if indeed the adaptive model outperforms the non-adaptive one in terms of better accuracy in the remaining useful lifetime estimation. And in order to test this hypothesis, we proceed along two steps. So at first, we took into consideration only the bearings of condition 1 to learn the parameters of a hidden semi-Markov model, that it is applied as it is, so in a non-adaptive way, to perform the remaining useful lifetime estimations on the bearings of condition 2. The second step we did is to consider the model based only on bearings of condition 1 and take it as a starting point for an online learning algorithm that continuously re-estimates the parameters of the model simultaneously to the remaining useful lifetime estimation performed on the bearings of condition 2. And as we expected, we obtain an improvement of the adaptive model with respect to the non-adaptive one in terms of better accuracy of remaining useful lifetime estimation of around 30%. We obtained also an improvement in case we swap the bearing of condition 1 and condition 2 for training and testing set. So, in summary, in this work, I propose the usage of a hidden semi-Markov model applied to the problem of remaining useful lifetime estimation. The main contributions are the usage of a parametric arbitrary distribution to model the state duration, which has advantages in terms of less parameter to be estimated. We introduced a new and improved induction formula which is able to estimate the state duration. And thanks to this formula, we obtain much better results in terms of accuracy of remaining useful lifetime estimation. We propose the usage of archaic information criteria to perform automatic model selection. And we completed the framework by extending the learning algorithm to work online. The output of these contributions are several publications that are listed here. And in particular, the last one, the last publication, derived from a work performed with my colleague Isabel Gonzalez concerning the application of this model, of the model I actually introduced in my work, to the problem of facial expression recognition, and in particular to the problem of the classification of the intensity of action units, where an action unit is a simple movement of the human face in an expression. So, for example, this slide shows the movement of the corner of the mouth in a smile. So, the goal of the work was to classify each frame of a video as belonging to one of 4 possible classes, where the 4 possible classes are the neutral, in which the action unit is not present, the onset, in which the action unit starts to appear, the apex, in which the intensity of the action unit reaches its maximum, and finally the offset, in which the action unit comes back towards a neutral expression. Concerning the future work, as I said before, in this work we used a gradient descent technique, which is quite easy and fast technique, to perform the online learning. However, future work should consider different optimization techniques, which might be also more accurate. As I said before, the archaic information criteria is not really a robust method to perform automatic model selection, especially in selecting the correct number of states. So a more robust method is needed, and a possible solution can be a combination of the archaic information criteria with the change point detection algorithm. Finally, despite time complexity was out of the scope of this work, it is really, really important, especially for methodologies that are intended to work online. For this reason, future work should carefully consider this aspect. So this concludes my presentation. I sincerely hope you all enjoyed it. And now I'm open to all your questions.